Imagine this. A billiard ball rockets across a table, colliding with another at just the right angle to sink a perfect shot. Professionals go for trick shots, nailing impossible angles with carefully planned initial strikes. It's cool for sure, but what exactly powers these precise, jaw-dropping shots? The answer lies in collision physics. Billiard ball collisions follow strict rules of momentum and energy, transferred during that split-second impact. In today's video, we're going to be taking a shot at modeling these collisions in Scratch, the first step to building our own virtual pool table and recreating those mind-blowing moments. Okay, before we can jump straight into coding this thing, we first got to get a few physics principles out of the way. Momentum is a physical property describing a mass in motion, which you get by multiplying an object's mass with its velocity. Energy is harder to explain, but it's basically the ability to do work, something I struggle with on a daily basis. In this case, we're dealing with kinetic energy, because the balls are in motion, and it's formulated by 1/2 the mass times the velocity squared. Billiard ball collisions are elastic, meaning both of these properties are conserved. So the total momentum and the total energy before and after the collision remains unchanged. Now that we know what factors we're working with, it's time to set the scene. First of all, we're assuming both balls have the same mass. Let's call the white cue ball A and the stationary target ball B. The initial momentum, by definition, equals to m times v0, and that equals to the final momentum, m times va plus m times vb. By canceling the common mass m, we get v0 equals to va plus vb, a simple summation. Now let's do that for the kinetic energy. The kinetic energy equals to 1/2 m times v0 squared at the beginning, and that equals to 1/2 m times va squared plus 1/2 m times vb squared after the collision. Again, we can cancel the 1/2 m on both sides, and we get v0 squared equals to va squared plus vb squared. Given we have these two conditions and two unknowns, all we need to do is solve for va and vb. But how do we do that efficiently? Let's take a closer look. Our cue ball A speeds towards and collides with the target ball B at an initial velocity v0. On impact, A exerts a normal force on B, in the direction perpendicular to the surface contact, which points from the center of A to the center of B. Because that's the only force exerted on ball B and by extension ball A, we know two things: that the velocity of B, vb, has to point in that direction, and that the component of v0 that points tangent to the contact is maintained in ball A, because there's no force exerted in that direction, and hence no change in that component of the velocity. That observation does a lot for us, because we're essentially transforming our initial 2D problem into a 1D problem. Remember those two equations we derived earlier? All we need to do is solve for the perpendicular component of the velocities such that it satisfies those two. In other words, v0 perpendicular equals to va perpendicular plus vb, and v0 perpendicular squared equals to va perpendicular squared plus vb squared. To save time, here's what it culminates to. va equals to v0 minus v0 dot delta s over the magnitude of delta s squared times delta s. And vb, by conservation of momentum, simply equals to v0 minus va. To clarify some terms, delta s is the vector difference between the centers of the balls, so that'd be the coordinate of A minus the coordinate of B. And the little symbol here is the dot product between the two vectors, where you multiply the x components and the y components together and add them. At its core, all these formulas do is change the velocity vectors in the direction of the collision force, making the balls deviate slightly off their initial trajectories. And remember how we assumed the target ball was stationary earlier? Well, the coolest part is we can actually generalize these equations to scenarios where the target ball is also moving by simply replacing the v0 as va minus vb and updating the velocities as follows. So va would be subtracted by va minus vb dot delta s divided by the magnitude of delta s squared times delta s. And VB is updated with the exact same term, except we're adding to it rather than subtracting. Alright, I know it's probably a lot to take in, but it'll make more sense when we see it in action. So let's jump into it. Alright, loading up a fresh project here, we first gotta get rid of that blank white background because that's kind of boring. So let's go ahead and choose a dark green color for our pool table surface, just like in real life. And I'm gonna use a little bit of a radial gradient here to give the edges a darker feel and make it look more realistic and stylish. Let's also name our backdrop pool table so we know what we're making. With the background done, let's go ahead and create our cue ball. To give the Scratch Cat some involvement in our project, I'm thinking we decorate our cue ball with the Scratch Cat logo, so it looks like it's zooming across the surface, nudging the other billiard ball. We can go ahead and cut out the body, create a white circle for our ball, and stick the Scratch Cat head smack dab in the middle like a cool skin. Now we just need another ball for the cue ball to hit. So I'm going to go ahead and create a new sprite, call it target, and create a red circle. Make sure it's the same size as the cue ball. And inside that red circle, I'm going to create a smaller white circle with a black number inside. I settled on number 5 because 5 is my favorite number. Picked a pretty reasonable font, handwriting looks pretty good. Now let's start coding the physics. First, let's create two variables, Vx and Vy, to track the horizontal and vertical velocity of our cue ball. I called it Vxa and Vya because we designated A as our cue ball. And then we have to set our initial velocity, along with creating our standard physics simulation loop, with change x by Vx and change y by Vy to update the position of the cue ball every frame. And there we go, we have our cue ball moving. Now let's do the same thing for the target ball, except we renamed the variables into Vxb and Vyb, because we designated the target ball as ball B. And the code is exactly the same, so I copied it over from the cue ball, except we change all the variables to the B version. Also, I forgot to name the project, so let's name it Billiard Collision. Time for updating our velocity. You might have noticed that our equation for updating the velocity requires this fancy operator called the dot product, so we'll need to define a special block for that. For any two vectors v1 and v2, the dot product calculates v1x times v2x plus v1y times v2y, and returns the value through this dot variable. Let's also create variables dx and dy to represent the vector delta s. Oh, but before we can do that, let's go ahead and insert an if statement with the touch block, just to detect when our cue ball is touching our target. So what this quantity is basically the difference between the position of the centers. So dx in this case would be the difference between the x positions, and dy the difference between the y positions. The beautiful thing about this formula is this entire portion is a coefficient used in all of our velocity update formulas. So we can actually just group it into a variable k and calculate it right away so we don't have to repeat code. Using that logic, if we break it down, we first need to calculate the dot product between VA minus VB and delta S. VA minus VB would be the difference between the x velocities of the cue ball and the target ball, so Vxa minus Vxb, same thing for the y. And delta S is dx and dy. Then once we calculate that, we can just divide the whole thing by the magnitude of delta S squared. That squared gets rid of the square root, so we're left with dx squared plus dy squared. Once we have that, we're ready to update our velocity components for our balls. Now it turns out we can actually just multiply k by dx and dy to update vx and vy respectively, and you can see why this is the case by multiplying both sides of our equation by cosine theta or sine theta. Vxa would then be added by negative k times dx and Vya by negative k times dy. And let's also do the same for our target ball, so that would be Vxb added by positive k times dx and Vyb by positive k times dy. Now if we set the target ball to the right of our cue ball and test it, you'll notice that cue ball fully stops while the target ball moves, and that is consistent with a perfectly elastic collision. If we try this instead at an angle, the cue ball is knocked upward while the target ball is moved downward, which is consistent with conservation of momentum. While we have our basic fundamental physics engine nailed down, we haven't accounted for a few more things. For example, friction. Our pool table should have friction, so what we can do is add a dampening factor on the velocity to slow the balls down as they move. Every frame the velocity would decrease by a certain percentage, say 1 or 2%. It's as simple as multiplying our x and y components of the velocity by this dampening factor for both the cue ball and the target ball. Let's try it out. So when I click the green flag, you'll notice that the balls actually slow down as they move, which is what we intended. The smaller the dampening value, the faster the velocities decrease, because we're multiplying by a smaller ratio. As a final cherry on top, let's make the billiards bounce off the edges of the screen, and that's as simple as just detecting if the X position or the Y position is in a certain range and flipping the X or Y velocity depending on if we're hitting the sides of the walls or the top and bottom. Alright, looks like the bounce is good to go. So that's it, that's our engine. Let's test different configurations and see what happens. Here we go. Alright, with that, we have a collision physics engine for billiards, 8-ball, and pool. Now a quick challenge to you all, remix the project in the description below, and try to make the cue ball controllable with the mouse and add more collidable balls for some extra fun. And if this video does well, I'll make some future videos turning this physics framework into a full-blown billiards 8-ball game, implementing features like making the ball controllable, adding more balls, creating pockets to score in, implementing spin to the balls, maybe even developing an AI player, or implementing multiplayer with cloud variables, even using the physics for air hockey too. Anyways, hope you enjoyed this video. Please like and subscribe, I really appreciate it. And if you have any solutions to the challenge or any extra features that you implemented to the project itself, let me know in the comments below and I'll go check it out. In the meantime, stay tuned for more coding and physics content, and I'll see you in the next one. Bye.